Right. I keep putting too much stuff on my phone, so I keep running out of recording. But okay, so it got annoying because I was trying to charge them, and the voltage was going up and then down. Now, I don't know if that's just simply something to do with the way the battery works when it's really, really flat, or if maybe there's an internal short which gets made during the charging process, which then will reduce the voltage again. So I don't know. So what I've done is, instead of attempting to do them in parallel, which ultimately I do want them to be, I thought, well, all I want to do is try and basically bring the voltage up. So what I've done is connected them in series, as you can see. So that means it's going to pass current through all of them, right? And I've set my voltage up. I've set my power pack up to cut off at 40 volts. Now the problem I've got is actually that might not be good, because I do know some of them are actually pretty flat, and then some of them have voltage on, like 2.5 volts. So I don't know if that's going to help. 40 volts would be 4 volts a cell, but if one cell is basically, or if a bunch of the cells are at 0, that means the other ones are going to be over voltage. So maybe I won't put it at that. In fact, I'm not actually going to charge it now at all. What I think I'll do instead is I can set it at something like, you can see what it's on at the moment, 11 volts, which is very low. And you can see the current I've got, which is 100 milliamps. So what I really need to do, obviously I need to monitor this for a start. And what I need to do is actually check the voltages as it's charging, which it is. You can see the voltage is going up slightly. 1127, there you go. So obviously some of these cells are accepting the charge, but then some of the others aren't. So I don't expect that to continue to rise. At some point it'll kind of flatline. But at the moment it's basically putting 100 milliamps in each one. Now these are, I believe they're 40 amp hour. So 100 milliamps is really pathetically small. The reason why these are lithium-ion. They're not the modern lithium polymer ones. That's the reason why they're actually really small, because the lithium-ion ones of the first generation that came out, they are quite small. Modern, the capacity of these is 40 amp hours, and the voltage of the cell is 4.2 volts, fully charged. Yeah, and so each one of those cells is, what is that, 320 amp hours? Yeah, but the lithium polymer ones that you get nowadays are, in the region of sort of 200 amp hours, and some of them are even smaller, because the putting the polymer inside it increases its volume. So for the same volume you get less capacity. So these are very high capacity compared to modern cells, but of course the opposite side of that is that if you get a dendrite going through it, right, which actually connects, because that's what happens, that's why they get fat. You can see those ones have actually filled out, right? Or maybe you can't, but they have. And that's the reason why they don't fit nicely like that. And what happens is inside they have dendrites from the plates, which connect across the plates. Now a thin haired dendrite will just frizzle away and die, but what happens is if a bunch of these things actually start connecting, then the inside of the cell then starts shorting out, and that has a compounding effect that it creates more dendrites, I believe, and so you basically get thermal runaway, and that's the problem. And the way this is why I'm not going to charge it now, because if I leave this on, it is possible that one of those cells could short internally and then basically cause a fire. Even though I'm only charging at a really low rate, the internal current inside the cell is what causes the thermal runaway, not the power I'm giving it, you see. And so if I charge those up to a capacity where they say, for instance, have, let's say they're 25%, and you then get an internal short, you've then got that 25% attempting to discharge itself in an instant, right? And this is a 40 amp hours, that's 10 amp hours. It's going to blow up. So that's what happens, and that's the reason why I'm not going to leave that turned on. I'm actually going to stop it now, because I'm going to go home, and I'll come back this tomorrow and I'll monitor it. A way to deal with this, of course, is to put sensors, thermal sensors on these, or like a thermal camera or something, because then you can see if they're getting warm. Because if they start getting warm inside, that means they're actually internally shorting, and that's the beginning of a thermal runaway, I believe. It's starting to rain now. So that's where I am right now. As you can see, the voltage has risen slightly, but I'm going to stop it because these guys I don't trust to charge without me being here, and I don't want this car burning down. I've had that before. So I'm going to stop that output. There you go. Yeah. Another way to do it is actually to shut the power off completely. If I put the power on and then just turn the current down to 0. Yeah. And then you can actually see, you'll see the voltage drop now, because it's actually not, the current is 0, so it's actually not providing current. Right, so there's no actual charging going on. But what it does is it then just turns this into a voltmeter, essentially. Yeah, you can see it dropping again. But I'm actually going to shut the output off. So it's actually disconnected. Yep. Still a bit concerned about these, because these are, I mean, some of them are, you can see some of them are actually sitting closely together, but like for instance, these 3 have got gaps between them, and these ones have got gaps between them, so they've got the problems. Yeah. Anyway. And the problem is, and the reason why I'm a bit concerned is because these things can internally short just by sitting there without actually doing anything. I believe. I don't know, maybe they won't. Well, maybe.